In this video, I'd like to continue talking about converting complex numbers between their polar and rectangular forms. And for this example problem, we have a complex number in its polar form, and we need to convert to rectangular form. And remember that the rectangular form for z1 is just the real part plus I multiplied by its imaginary part. And also, the complex form of z1 is equal to the magnitude, or the absolute value of z1, multiplied by the cosine of the angle theta plus I times by the sine of the angle theta, where theta is measured from the positive real axes. So we have a complex number whose magnitude is 4, and remember that's just the distance the number is from the origin, and the angle is 11 pi over 6, which notice is slightly less than 12 pi over 6, which is 2 pi, which if we have an angle of 2 pi, that takes us all the way around. So this angle is slightly less than that, meaning that our complex number is roughly, let me redraw that, right about here in the complex plane, maybe give or take a little bit in terms of its angle, but this distance here is 4, and like I mentioned, this angle here is 11 pi over 6 radians. Now, the goal of this is to convert this to rectangular form. So let's start by rewriting z1. We have that 4 is multiplied by the cosine of 11 pi over 6, and we will add I times 4 multiplied by the sine of 11 pi over 6, and essentially I just distributed the 4 to each of these terms so that we can actually simplify, since this part right here is our real part, A, and this part right here is the imaginary part, B. So if we can evaluate the sine and the cosine of that angle, then we can simplify everything. But we need everything in exact terms, so we can't just plug these straight into our calculator and get a decimal answer, since both of these are irrational and we'd have to round them. But to get the exact answer, we can consider the unit circle. And with the unit circle, remember we have a radius of 1. This is not drawn perfectly to scale, but we need to determine where this angle is, and we know just by thinking it through that it's going to be somewhere down here. And with the unit circle, we also need to remember that for the x and y coordinate, that x is the cosine of the angle and y is the sine of the angle. Now, this angle 11 pi over 6, this is one of the special angles, and it's a multiple of pi over 6. And remember that pi over 6, that's just a 30-degree angle. And if we want, we can convert 11 pi over 6 radians to degrees. It's essentially 360 minus 30. This is a 330-degree angle. But knowing that this is a multiple of the 30-degree angle, if we analyze the 30-degree angle in the first quadrant, we can look at that triangle and its x and y coordinates, and the angle that we're actually dealing with, this 11 pi over 6 radians, would have the same x and y values, but y would be negative since we're in the bottom half of this plane here. So let's focus on this triangle, and when we draw that triangle, we would have a 30, 60, 90 triangle, where this one is the 60-degree angle. And since we know the hypotenuse is 1, and if we remember the pattern for a 30, 60, 90 triangle, that it's half of an equilateral triangle, then the side opposite the smallest angle, the 30-degree angle, is half the hypotenuse. And from here we can use the Pythagorean theorem, or just remember the pattern, that the side opposite the middle angle, the 60-degree angle, is 1/2 the small side multiplied by root 3. So for this triangle, its horizontal component would be root 3 over 2, and its vertical component would be 1/2. And there are other ways to remember these special angles, but ultimately they come from special triangles, the 30, 60, 90 triangle, or if we had the 45-degree angle, it would be the 45, 45, 90 triangle. And for our coordinate, we just need to realize that The y value is negative since we're in the bottom half of the plane, but the x value is still positive. So we get root 3 over 2 for the cosine of 11 pi over 6, and minus 1/2 for the sine of 11 pi over 6. And with these numbers, we can plug them into our formula. So that z1 is 4 multiplied by the cosine of that angle, which is root 3 over 2. We have plus I times by the sine of 11 pi over 6, which we know is minus 1/2, and we're multiplying all of that by 4. And we can simplify this. 4 over 2 is just 2, so we get 2 root 3, and 4 over 2 here is also 2, but we have a negative, so we get minus 2 times I. And there are a couple ways to verify this. We can compare the decimal for this with the decimal for 4 times by the cosine 11 pi over 6 if we put that into the calculator. Or we can also use the formulas. We know that the magnitude of our complex number is just the square root of the real part squared plus the imaginary part squared, and the angle is the inverse tangent of the imaginary part divided by the real part. So there are various ways to check this, but visually speaking, if we converted these to decimals, we would see that we would have this point right about here on our plane, where again that length from the origin is 4. It would have a real part of 2 root 3 and an imaginary part of minus 2i.